Hi guys. So today in the class, of course I talked too long, and so we ran out of time taking notes, so I wanted to finish them, and then I thought I'd just talk through them real quick so that we had all of them talked through for the people who are gone. So today we talked about making predictions using our least squares regression line. And so remember this little hat, the little caret thing over y? That means the predicted y. We call it y hat. And we want to use our variable names. Remember, we used atomic mass and atomic number in our example. Be careful with extrapolation. Remember, extrapolation is when we're going way far outside of our data set, often to predict something like out in the future. And sometimes what happens is our model maybe doesn't work, or maybe our model is only valid for kind of around the data that we started with. So anything outside of our data set, we always want to treat that with caution. The next thing we learned about were residuals. So residuals are kind of like the little leftover piece, and they are our actual value minus our predicted value. So residuals show up on our graph by just being like the little difference between our true value, which is showing up as our scatter plot, and then the predicted value, which is where it would land on the y equals mx plus b equation, or a plus bx equation. There we go. The least squares regression line. That's a hard thing. So the next thing we were talking about, oh yeah, this is our sentence stem is what it's called. So if we need to predict, or if we need to interpret a residual, I was obviously running out of time because this is for interpret a residual. If we need to interpret a residual, then we want to say the actual, so like the actual atomic mass for tungsten was 1 point, I think it was 1 point, I don't remember, 1.8 or something higher than predicted for x equals 74, for an atomic mass of 74. So whenever we interpret a residual, we sort of want to use the sentence structure with our context, and then residual is a number, and then we give that x coordinate. Okay, so the next part that I wanted to talk about is if we need to interpret both slope and our y-intercept. So y-intercept and slope. So let's make sure we get these sentences written down. They'll definitely make our life easier when we're taking quizzes and things like that, so that we make sure that we get all of our points. So for our y-intercept, I wanted to put it in a little box so I could find it. What we want to say is when x is 0, and whatever that is in context. So in our case, we were using our x was the atomic number. So when the atomic number is 0, the predicted, and predicted is always super duper important in this particular section of stats, because we are really emphasizing that these are our predicted values versus our actual true measured values. So the predicted y context, so in our case, this was the predicted atomic mass, is, and I think mine was in class today, I think it was negative 4.6 or something silly like that. So sometimes the y-intercept doesn't make sense. So if it doesn't make sense, and we are asked to interpret it, then we should definitely note that. And so if you were asked to interpret that atomic mass, and you're like, you know what, we really shouldn't have a negative atomic mass. This probably should be closer to 0. We would just kind of want to say that in our interpretation, because that's the whole point of interpreting it, is so that someone knows sort of our thoughts behind it from a statistician perspective. The other part is our slope. So if we need to interpret our slope, then what we want to talk about is with each additional, oh my goodness, that's supposed to say each. With each additional x value, and remember from class today we were using atomic number as our explanatory variable. So for each additional atomic number, we predict, or the predicted, and again, predicted is very important to make sure that that makes it in our sentence, because we want to note that they don't always, it's not a guarantee. And the predicted Y context, so like the predicted atomic mass, increases or decreases. Obviously, it's the sign of our slope that tells us that, by whatever our slope is. Okay? So let me know if you guys have questions for that. But really, with these interpretations, I'm not looking for you to rewrite the sentence, but rather just sort of, as you practice doing your homework, just use your notes and use a sentence structure so that as you write it, you just get used to saying it in that way. And then that's how we can remember it. And then that's how we remember it for quizzes and whatnot. Okay. The last couple things I wanted to talk about were our least squares regression line. So this LSRL stands for least squares regression line. And sometimes it's a little confusing, like teachers are like line of best fit, least squares regression line, and they all just kind of like meld together to this like weird, like I have a scatter plot and I want a line to go through it. So that is all kind of true. The least squares regression line technically is a very particular type of a line of best fit. So if we imagine that this is our like data set, and it's a pretty contrived data set, but that's okay. And this is our line, that's our least squares regression line that runs through it, or our line of best fit in this case. What we talked about today were residuals. And so residuals are these little distances here, okay? And so we use those to sort of measure how good of a fit it is, right? And so we might think about it. We have a line like this, and I'm just going to make a very simple line. It's like 1, 2, 3, okay? And this has a residual of +1, and this residual is -2. Okay, so the residuals kind of balance out to 0, right? Let's say we have another one, and here's our least squares, or here's our regression line. And this one has, where do I want to go with this? I was trying to basically give us this idea. Oh, here we go. This is what I wanted to do. I wanted to do more points. 1, 2, 3, 4, 5, 6. If I do like this, and I do a bunch of points very close, right? This ends up being 0. Sort of differences, right? I have the equal, above, and below. Here, say my data was all like just further spread out, just still a good fit, but it's just like way further spread out. So each of our residuals is bigger. We kind of want to account for that somehow. So what our least squares regression line technically means is that we have all of these residuals and you square the residuals. It helps make them positive. It helps sort of give more weight to the ones that are further away. And what that does is the one that gives us the smallest total area of all these little squares on it, that is the one that is our least squares regression line. So it's just a particular line of best fit that sort of minimizes the sum of the squared residuals. And that's a big mouthful. And it's not something that you are ever going to have to actually calculate or do, but it's something that we should kind of understand, that it's making those residuals squared the smallest overall. It's a long kind of gross calculator problem, so that's why we always use our calculator or a computer to find our least squares regression line from the data. Always use calculator or computer. Now there are a couple more things that we're going to learn about our least squares regression line if we have some very specific information about our data set. There's some ways we can find our slope and then our y-intercept based on properties. But in general, if you have data, you're going to use your calculator. You're never going to be expected to do that by hand. Let me know if you guys have questions on that. The last thing I wanted to talk about were our residual plots. This was where we were sort of getting to at the end of class. So residual plots are when we take and we graph still our x on the x-axis, our x variable, but on the y, we graph the residuals. So remember that was like all of these little values that are how far away our point is from the line. Those become our y values. So positive is above the line, negative is below the line, okay? So what we want to see is a nice random scatter in our residual plot. We don't want to see a leftover pattern. We just want to see like random dots. So this is good. Random scatter and no pattern. And that no pattern, that's a big one. The biggest concern in a residual plot is a pattern. So a bad residual plot would be something that looks like this. So see how it goes positive, negative, positive, and it makes this nice curved pattern? That is bad in residual plot. This is a leftover pattern. That means that our data is likely not linear and we have the wrong model. The only other issue that we really get into with residual plots is sometimes you'll see this and it's called fanning. And what it is our model starts out pretty good, and then as time goes on, our model gets worse and worse. And see how we have created this sort of like triangle or fan shape where as x increases, the residuals increase. So that's going to be an issue because it means that our model is not equally good for all x. We predict really well down here, but we don't predict well out on the end. So model not equally good for all x. And so that's going to be concerning to us as well. It'll also tell us that when we get out here on this far end, that we should probably be very cautious about using our model because our residuals are just all over the place. Okay, so those are all the notes for today. So if you were in class today, then our homework is this CYU and also this CYU, and I will triple check that they are in the in Schoology, and I'll also make sure I post the solutions. And then Friday, you guys will be doing these problems, which are out of the book. So they're all related to today's notes. So let me know if you guys have any questions or need anything. And other than that, have a good day.